Howdy, welcome back. So the strategy pattern. I'm going to go ahead and introduce it using the vocabulary from Professor Zillis's slides, and then I'm going to go ahead and share with you I guess, example of its implementation that is derived from an exam question I used to give in my 121 course at Texas A&M University. And it is I'm not going to give you the whole question, but it is kind of interesting, and it was actually provided to them without any explanation as to this was the strategy pattern. It was just simply, what is kind of the output of this? And it relies heavily on abstract classes. I made use of inheritance. You'll see it'll, I hopefully be fun. But here's the idea behind the strategy pattern. Let's define a family of algorithms, encapsulate each one, and make them interchangeable. So the strategy pattern is going to let the algorithm vary independently from the clients that use, say, some particular object. What does all this mean? Just kind of think in terms of, we're going to have some different behaviors. Somehow they're going to be interchangeable, and something's going to own them or use them. So let's see where we're going. So when to use this strategy, and it might not be as intuitive right now until after the example, but I'm going to go ahead and present this up front. So use the strategy pattern when many related classes differ only in their behavior. You need different variants of an algorithm. An algorithm uses data that maybe the client shouldn't know about, so we're going to go ahead and encapsulate the algorithm data from that client. Or maybe a class defines multiple behaviors, and these are kind of implemented with conditionals, that is some sort of check on an attribute. It might make more sense to employ this strategy to get around perhaps some of that. So the solution here's going to be the strategy pattern. We're going to have a strategy abstract base class, which is going to expose the interface to our algorithms. We're then going to have some sort of context object, which is going to have a concrete strategy. And the context object is going to invoke the algorithm through its interface, and thus would interact with a particular strategy. So I took this diagram from Professor Zillis's slides. So here's some of his handwriting. So something is going to have maybe a strategy. So what can a strategy be? It can be approach on how we might do something. So if you're playing cards, and this is going to be a terrible example because I do not play cards, but I would assume there's very different strategies. I don't know why, but Monopoly popped in my head. So maybe one strategy, so think about this as maybe the game player for this example, and you're playing Monopoly and you need a strategy. Well, how can we associate a person maybe within our application with a particular strategy? Well, we could have this strategy thing that defines, well, it doesn't define, but it lists the different ways that we'll be able to interact with a particular strategy. This will be an abstract class, which is simply introducing the interface to how we can interact with a particular strategy. And then derived from that, we can have very different implementations that will constitute a well-defined strategy. So instance, maybe strategy A is just buy everything. Everything you land on, just buy it. So this is the Monopoly example. Strategy 2, I don't know, maybe you buy things if it's a certain location on the board. I don't know the Monopoly strategies. I'm just thinking out loud here, and maybe it's something like that. But anyhow, what you can see here is whether it's cards, Monopoly, other games, etc. There's different strategies that can employ it and how we can accomplish various ends. And it could be the case that we might want to have different strategies associated with different entities within a program. And I'll get onto that bit more in a moment here, but hopefully you can see the requirements of this. A particular game player, context object, whatever you'd like to call this, is going to own a strategy. It's going to have a strategy. It will be composed of a strategy. And then we have this abstract base class. And again, from that we'll derive concrete strategies. So concrete strategy A is going to is going to be, so it is a strategy. So if you start thinking about this, well, if this is the interface, and what if we did something like strategy? Maybe S is a better word. Something like S is a pointer to a strategy, so pointer of the base type. Remember, that's okay, even though it is an abstract base type. And we're going to initialize it with the address of a new strategy object A residing on the free store. Well, if strategy provides the whole the whole interface to how we can interact with any any concrete strategy object, well, you could start to do stuff like S. I don't know how do we invoke a strategy in our gameplay example? S do strategy. Let me use the correct casing here. I don't know, something like that, right? But the key thing to note here is that if this interface is defined in the abstract base class, not defined, sorry, if the interface is afforded through the concrete base, or sorry, through the abstract base class, and if these are pure virtual function declarations, every concrete strategy would have to implement that behavior, and we could access the child's behavior, so the concrete strategies implementation, through that idea of virtual functions. So hopefully this is all coming together now. I know this is going to probably take a bit longer than I expected. Let's run through it. So here's the old exam question. Previously, you established a class hierarchy of birds through an is-a relationship. Each bird implemented its own version of perform speak because birds make different sounds. So the idea was you had this like super bird class, and then maybe you had a penguin, a blue jay, and some other bird. And each one implemented its own version of perform speak. So I don't know what the penguin noise is. I'm not going to try to do it here. The bird, blue jay might chirp, and I don't know where we're going from there. But again, each specific type of bird had its own way of speaking. However, the question becomes, what if we wanted birds of the same type to speak differently? So in the code that follows, and I'll share this with you, we define a duck that delegates its quacking behavior to another class instead of using behaviors that are defined in the base class and overridden in the derived class. So what we're going to see here is a particular duck is going to own a quacking behavior, which will dictate how that particular duck speaks. So maybe we have one who's a quiet, more chill duck, and it does a quiet quack. Maybe we have a more awake duck who's rowdy and just quacking away loudly at that. But anyhow, we'll look at like how, and they're all a duck. So maybe we have, how can we make them speak differently? Well, what we're going to do is say that a duck has a quack behavior, and we will provide that behavior by composing a duck with the quack behavior that we would like it to have. So going back to our strategy pattern, the strategy is going to be a quack behavior. The duck is going to have a particular quack behavior, but quack behavior is abstract. It's like animal, if you remember that example where I tried to give, where it's like, well, what is an animal? It's abstract. It's not a thing. You'd ask what type of animal. Same thing's going on here. Quack behavior is abstract. It will simply provide the interface, which will just be one behavior. I can't remember what its name, but we'll see on the next slide. But each of the different quacks will have like loud quack, quiet quack, silent quack, or something of that nature. Each of them are going to inherit from quack behavior, and they will implement the virtual functions that are required that they do so by their parent class. And then we can just interact. It doesn't matter if a duck would have a pointer to a quack behavior, and it could be a pointer to concrete strategy A, concrete strategy B, concrete strategy C, or through that example, a loud quack, silent quack, or no quack. So here's our quack behaviors. We're going to see here's the abstract base class. And we know that because it has a pure virtual function, quack, which means that every quack behavior is guaranteed, or sorry, every quack behavior object that is derived from this parent. So every child is going to have to implement that quack. So it means that if we're looking at any of the children through the lens of the parent, they're all guaranteed to quack because quack was declared as a pure virtual function in the parent, which means that in order for anything that derives it to be a concrete type, they must provide an implementation for that behavior. So we have loud quack over here, which is just going to return a string, and it's going to be this, I don't know, shouting quack. So quack in all uppercase letters. Quiet quack is, I don't know, we're on computers, so it's all lowercase letters. But notice here, it's going to inherit from quack behavior. It's going to go ahead and become a concrete type by implementing the pure virtual function declared within its parent. So now we have a definition for quack for quiet quack. And then there's no quack. And that's just, I guess I could have done like chirp or something, but that would return the string silence. Okay, so we've got our strategy, that interface, it's up here. Then we have our concrete strategies here, which are that loud quack, quiet quack, no quack. Okay, now let's look at our ducks. Hope we're doing okay on time, but let's go ahead and look at this. So just to make the question fun, I threw some inheritance at my previous students, and I said, okay, we're going to have a duck, and it is going to store a quack behavior, so a pointer to a quack behavior. And then here's the interface with our duck. So it'll have a parameterized, a default constructor, which would initialize quack behavior with no quack. That's default for new duck. We'd also have a parameterized constructor that would take a pointer to some sort of newly allocated quack behavior. So an object of this type. Okay, our virtual destructor, would be defined as freeing the memory associated with quack behavior, assuming that the quack behavior data member points to an object residing on the free store. And then we have these fun functions, set quack behavior, which would essentially deallocate the previous quack behavior, provided it existed, and then go ahead and assign quack behavior to some sort of new behavior that was passed into the setter. And then if we want the duck to perform quack, we're going to return quack behavior, quack. So if we had quack behavior pointing to loud quack, quack would be returned. If we have it pointing to a quiet quack, quack would be returned. And then if it's pointing to no quack, we'd have silence. And then we have a couple of different types of ducks. This again was to kind of make it fun. I had a mallard duck whose default constructor was a nice quiet quack behavior. And then I had a rubber duck, which utilized the default constructor of the duck type, so it had no quack. And understand that at this point, part of this question that I was asking was, can you read through this and figure out what's happening, what constructors are being called where, how things get set up. And I even had some other questions pertaining to like, hey, we don't really have a duck per se. There's types of ducks. So how could we make duck an abstract base class? So, I mean, these are all things you need to start thinking about and putting together. So we've now introduced, we have our ducks, and there's actually some subducks. We have like mallard. Then we also have rubber. And then we have our quack behavior, quiet, Loud, no quack. Cool. So here's where we can actually see the strategy now in action. So let's create a vector of pointers to duck objects, and let's push back a new mallard duck. So the new mallard duck, its default quack behavior is the quiet quack. We push back rubber duck, whose default quack behavior is going to be silence. And then we could go ahead and say for I is equal to 0, I is less than duck size. Maybe I should have done a for range-based for loop here. We can ask each duck to perform its quack. And we see quack and silence. Now here's where things start to get interesting, because each duck, so one mallard duck could quack differently from another mallard duck, depending on the strategy that a particular mallard duck employed. And we can see that by saying duck's at 0. I'm going to set its quack behavior to a new loud quack. And the next time we ask that duck to perform its quack, we see a loud quack. And then because we didn't do anything with rubber duck's quack, I was going to change its behavior, but I'm like, it's an inanimate object. It probably doesn't make sense to. So it's just going to continue to be silence. But again, this is where it's cool. Each duck can employ its own strategy in terms of how it would like to speak, and that can vary across even the same types of ducks, or you could have a mallard duck and a rubber duck speaking both in silence.